Okay, let us start. Yeah, so we have seen the definition of an equivalence relation in the class. Yeah, it's a binary relation, which means E is a subset of A cross A, where A is any set, and it is an equivalence relation if, all of you know this, it is reflexive, symmetric and transitive. One simple relation is the diagonal relation. Yeah, so diagonal relation is denoted delta sub A. Yeah, that is an equivalence relation for any set. Right? So delta sub A is simply the elements on the diagonal. So you can check it is reflexive. Yeah, this an equivalence relation cannot be empty unless the set is empty. Correct? Because these pairs always have to be there. The second and third conditions are conditional. You understand? If A is related to B, then B is related to A. You don't force A to be related to B. However, the first one is forced. For all elements A of capital A is related to A. Right? Similarly, third condition is not forced. It's also conditional, if-then type of statement. So, this diagonal relation must be contained within contained inside any equivalence relation by condition 1. Understood? Yeah, so give me some other examples of equivalence relations. Suppose let's talk about integers. Do you know any equivalence relation on integers?
Like the one we defined in class.
Hmm?
The one we defined in class 8, so
Ordered by?
Yeah, A plus D is equal to B plus C.
No, that's on pairs of integers. We want something on integers themselves.
No, that's on pairs of natural numbers.
That's on pairs of natural number. Okay, fine. We'll come back to that perhaps. So on Z, say A is n equivalent to B if A minus B is a multiple of n. Yeah, here I am saying fix n, which is a positive number. So A minus B is a multiple of n. Is this reflexive? Yes, A minus A is 0, 0 is a multiple of n. Is it symmetric? Is it transitive? Yes, so this is an equivalence relation. The equivalence classes are called the modularity classes, right? So the equivalence classes, we haven't yet defined equivalence classes. Let me do that again. So let me see if I have some other example written down. Okay, so I will recall something, yeah, on n cross n. Yeah, we defined this to be an equivalence relation. A comma B related to C comma D if A plus D is equal to B plus C is an equivalence relation. Correct? This we have seen already. Then on the class of all sets, tilde like equinumerosity is an equivalence relation. Right? Because A is equinumerous with A for any set A. If A and B are equinumerous, then so are B and A. If A is equinumerous with B, B is equinumerous with C, then there exists a bijection between from C to A as well. Right? So just the composition. So we have seen all these examples. Even for construction of rational numbers, we had something. Yeah, some equivalence relations on pairs of integers where the second component is not allowed to be 0. So there are many equivalence relations. In fact, I'll give you one more example. Given a surjective function f from A to B define A1 related f related to A2 for A1 A2 in A if f of A1 is equal to f of A2. Okay, so this is also an equivalence relation. Then tilde f is also an equivalence relation. Observe that A is related to A because f of A is equal to f of A. If f of A is equal to f of B, then f of B is equal to f of A. Equality is an equivalence relation, right? So therefore, this is like pulling back equality on B as an equivalence relation. What is equality? Equality is simply the diagonal relation on B. Diagonal delta B we saw. Yeah, we can pull back an equivalence relation from codomain to domain. I am saying surjective, although it is not really necessary. Understood? This is an equivalence relation. In fact, every equivalence relation gives rise to a surjection. Okay, so this was the fourth example. I am going to claim every equivalence relation on A gives a surjective function f, every equivalence relation, let me label it E, then it gives a surjective function f from A to some B, for some B, that depends on E. What is this B? It is the set of equivalence classes of E, right? So let us define that. Yeah, so the equivalence class of A in A is defined as this set, all those B's in A such that A holds. In other words, all those B's in A such that the pair A comma B is in that equivalence relation. So this is a set. Obviously, we are taking a subset of A, capital A, and all those elements which are related to A, small a. So this is a subset. Okay, so this is full stop, and define A modulo E to be the collection of all those equivalence classes such that A is in A. So I will ask you a simple question. Yeah, for example, given A equal to 1, 2, 3, 4. Yeah, and E equal to 1, 1. Obviously, I have to put 1, 1, 2, 2, 3, 3, 4, 4. I don't have any option, right? Then I will add 1, 2, 2, 3, 1, 3, then 2, 1, 3, 1, and 3, 2. This is an equivalence relation. Yeah. So because it's reflexive, transitive, I closed it under all the properties which are necessary, and then this is comma. What is A mod E? I mean, ideally speaking, it contains equivalence class of 1, equivalence class of 2, equivalence class of 3, and equivalence class of 4. What is equivalence class of 1? 1, 2, 3. Then what is equivalence class of 2? 1, 2, 3. Equivalence class of 3 again 1, 2, 3. So I don't have to write it 3 times. By axiom of extensionality, yes, extensionality, this is precisely just a 2 element set like this. Okay, it has only 2 subsets 1, 2, 3 and 4. And then clearly, do we have a function from A to A mod E? Yeah, so and Fe from A to A mod E, yeah, this is a surjection, we can check that, where little a maps to the equivalence class of A. Clearly, every element of A mod E is of the form class of A for some A. So therefore, this map is surjective. So yeah, I mean this is also well defined, small a maps to class of A. So you understand A is 4 element set in this example, and then this is 2 element set. 1 from A maps to 1, 2, 3, 2 maps to 1, 2, 3, 3 maps to 1, 2, 3, 4 maps to 4. That is the map. So this is called a surjection. Yeah, I mean this is not called a surjection, you already know what the surjection is. But this surjection, if for this particular surjection you do whatever is written in the first line. Yes?
Did you write it set of 1, 2, 3, set of 4?
Because what is the equivalence class of 1? 1, 1, 2, 3. Equivalence class of 1, look at this definition. All those elements which are related. So observe here, 1 is related to 1, 1 is related to 2, 1 is related to 3. So therefore, which B's can I choose? 1, 2 and 3. Right? Okay, so given this map from A to A mod E, if you define this equivalence relation as it was done in the first line over here, you will get back the equivalence relation. Okay, so given this particular surjective map, what will be the corresponding relation tilde f sub e? This is f sub e. So what will be tilde f sub e? Well, it will be equal to E itself. Okay, so it's a perfect one-to-one correspondence between equivalence relations and such quotients. Surjective maps with domain A are called quotients of A. However, there is a catch, it's not a perfect one-to-one correspondence. Any questions so far? Okay, let's go ahead. So, given an equivalence relation E on A, and a bijection G from A mod E to B. All of you understand A mod E now? Yeah, B is any set and there is a bijection between A mod E and B. Okay, then what can you say about the relation tilde of with tilde has a parameter, yeah, please observe tilde sub f, we are defining tilde with respect to a surjective function. So I am going to write down the function g composed with fe. What can you say about this? So let me write it down. So you have A, then from A there is a surjection f sub e onto A mod e, and now there is a bijection G from A mod e to B. So now what can you say about G composed with Fe? It is surjective, yes. It is surjective, so for every surjective map we have a tilde relation associated with that map. What can you say about that? It will be an equivalence relation obviously, but which equivalence relation? Well, you only know one equivalence relation to begin with, capital E, yeah. So we have, so what is the answer? Tilde GFE is equal to E. Okay, so let me try to show you why. Yeah, if you are confused, so let A1 and A2 be in A. Then if A1 is related to A2, then what can you say about Fe of A1 is equal to Fe of A2, and therefore GFE of A1 is equal to GFE of A2, and therefore A1 is GFE related to A2. And I can also trace it back because G is bijective, I can cancel it from this side. Yeah, I can start with this, therefore this is true, therefore the previous one is true because G is bijective, therefore A1 is related to A2. Understood? So now you understand what I am saying, that if I have a quotient, I have one map, yeah, this is one quotient onto B1 and another quotient onto B2. Okay, this is my G1, this is my G2. Then actually both of them will give me the same equivalence relation on A, provided there exists a bijection between B1 and B2. So such bijection, yeah, I mean B1 up to a bijection, that is called a quotient. Quotient is not a single surjective map, but it is such equivalence class. Yeah, it's not just this. If there exists an H, then they both give you the same equivalence relation. If there exists a bijection H, then the equivalence relation is the same. We just proved that. Okay, so a quotient. So given surjections G1 from A to B1 and G2 from A to B2, say that G1 is equivalent to G2 if there is H from, well, I am writing it from B2 to B1, but you can as well write it from B1 to B2 such that H composed with G2 is equal to G1. Then this tilde equivalence classes of surjections with domain A are called quotients of A. Yeah, one quotient is not just one map, but it is such equivalence class of maps. Because see, everything is just changing up to bijection. Bijection is renaming. Well, renaming doesn't really affect the structure of the function. Yeah, that's why we are saying this is a quotient. So if you remember, the exercise sheet said that there is a one-to-one correspondence between equivalence relations and quotients. So this is what a quotient is. And there is one more thing which is in bijection with equivalence relations, that's partitions. Okay, so a partition, yes? This is the definition of quotient. Okay, a partition P of a set of a non-empty set, let's make it non-empty. A. So what is a partition? It's a collection of disjoint sets, yes.
Whose union is the set itself.
Is a set P such that union of P is equal to A, and for all P1, P2, small p1, p2 in P, P1 intersection P2 is empty. Right? This means that every element of A lies in exactly one element of P. Yeah, that's a partition. So clearly, A mod E is a partition of A. Right? So what we are doing? We are starting with A, we have some elements A1, A2. Suppose A1 is related to A2, A2 is related to A3, and then we put them in the same partition. This element is put in its own partition. So this is a partition of A. Right? So this simply says that A1 is related to A2, A2 is related to A3, and so on. So this is a partition. Conversely, given a partition, we can define an equivalence relation. Yeah, so given a partition P of A, define A1 P related to A2 if there exists some small p in P such that A1 belongs to P and A2 belongs to small p. So A1 and A2 are both elements of the same part of the partition. Yeah, so clearly, yeah, I mean clearly, I am writing clearly because A and A always belong to the same partition. If A and B belong to the same partition, then so do B and A, and by transitivity, yeah, everything is perfect. Yeah, so clearly, tilde P is an equivalence relation, and I invite you to prove this next statement, that the following sets are in bijection with each other The first one is the set of equivalence relations on A for each set A. Okay, the set of equivalence relations, the set of quotients of A, and third one, the set of partitions of A. Set of partitions of A. So, first of all, like, why is the collection of equivalence relations on A a set? Every equivalence relation is a subset of A cross A, which means it is an element of power set of A cross A, and therefore the collection of all equivalence relations is a subset of the power set of A cross A, and hence an element of the power set of the power set of A cross A. So it is actually a set. So you can check that these three things are in one-to-one correspondence. This is a lengthy proof, but straightforward. Please make sure you write it by hand. Okay, let's go back to the first one. So here in 2, can you identify, so in 2, Z mod triple N is the ring Z mod NZ. Have you seen this notation? Yeah, Z mod NZ. How many elements does it have? N. N, not n minus 1. It has n elements, and yeah, together with a map from Z to Z mod NZ. What is that map? Well, every integer m maps to the class m plus nz, right? Okay, the equivalence classes here we already know they are called integers. The equivalence classes here, equinumerosity classes, and the equivalence classes here, singletons, right? The equivalence classes for this are precisely singletons. So you look at this definition of a partition, right? So the partition in that case would be, I am just going to use this red color, and over here I am going to write the corresponding partition is singleton A such that A belongs to A. Correct? Yes.
So in the next slide,
Second?
yes, in the column sheet you have defined any surjection to be a quotient, and here you are defining
No, I am saying, no, I have said that a quotient is an equivalence class of surjection.
In the column sheet you have defined like any surjection to be a quotient. In the column sheet, and you have defined like
Both of them are okay, yeah, but let's choose this as the definition, yeah. One surjection and then equivalence class, let's call it the quotient. It doesn't really matter, yeah. The underlying meaning is still the same for both of them. Okay. Yes.
Sir, how did you prove that tilde f is equal to e?
Tilde f is equal to e over here. I proved something more over here. So just take G to be identity and then follow the same proof, you will get tilde f is equal to e.
If A1 is A1 E A2, then you write FE A1 is equal to FE A2.
That is the definition of Fe, correct? What is Fe?
No, sir, but here it is written A1 E A2, not A1 is tilde FE
Yeah, but that will be the conclusion and it goes both ways, right? See, if this happens, then this happens, then this happens, then this happens. That is also true. Yeah, actually, maybe I should write it down here that these are bi-equivalences. Yeah, can replace. I said that orally, I did not write that. Can replace therefore by equivalences, and therefore it is true.
So FE-A1 is equal to FE-A2 implies A1E-A2.
Yes, that is the definition of FE. Please check. What is FE? FE of A is precisely the equivalence class. So two elements have same equivalence class if and only if they are related, they are E-related. Okay, so these are equivalence relations. Equivalence relations are very natural in mathematics. Yeah, sometimes you also require your equivalence relations to be compatible with algebraic operations or relations, other relations. Yeah, so then they are called congruence relations. So for example, this particular relation that we had here, yeah, this particular map, this also behaves well with respect to addition. If I take M1 and M2, then the class of M1 plus M2 is also the same as class of M1 plus class of M2, and multiplication of classes also works nicely. So this is actually a congruence relation for the ring structure. Yeah, so equivalence classes relations satisfying more properties are actually required in algebra, topology and so on. Yeah, those are known as congruence relations. Okay.